This is the regulation of the blood pressure and the other problems with the regulation with the help of the, first of all, autonomic nervous system and some hormones. This is the plan which explain the effects on the heart of the sympathetic nervous system and the parasympathetic nervous system. The sympathetic and the parasympathetic nervous system change the heart walk, and we have the 5 effects: inotropic, chronotropic, bathymotropic, dromotropic, and tonotropic effects. What is the inotropic effect? This is from the ancient Greece language. Inos. Inos, this is mean in the English, this is the power, force. This is the change of the force of the power of the heart contraction. Then the chronos. Chronos, this is the time in English. Bathmos. Bathmos, this is the excitability. Dromos, this is the excitation conduction, the rate of excitation conduction. And tonos, the same, this is the tone in English language. All these processes are changed with the help of the sympathetic and the parasympathetic nervous system. But these changes have their peculiarity. Their peculiarity is based, first of all, on the peculiarity of the innervation of the heart. This is the heart with 4 chambers, and this is the innervation of the parasympathetic nervous system. The 2 vagus nerves, left and right, innervate the heart. But the feature is this. The 2 vagus nerves innervate only the both atria. That's why the effects, first of all, results in the change of the walk of the sinoatrial node, which have the automaticity, and the atrioventricular node. That's why the parasympathetic nervous system affects, first of all, to the chronos, the frequency of the heartbeat rate, the rate of the excitation conduction, and the rate of the excitation conduction, dromotropic effect, and the excitability. All effects are negative. At the same time, decreases the force, but this is the secondary effect of the parasympathetic nervous system, and decreases the tone. First of all, the vagus nerves decreases the rate of excitation conduction, decreases the excitability of the heart, and decreases the frequency of the heartbeat rate. Sadipur Ma Bina, you should switch on your video, all right. And the sympathetic nervous system, the neurons remind you, are located in the 12 thorax segments. Then they have the transmission in the vertebral sympathetic chain. This is acetylcholine effect to the N-choline receptors. In the intramural ganglion, the same acetylcholine and N-choline receptors. At the end of the parasympathetic nervous system, acetylcholine and M-choline receptors. More precise, M2 choline receptors. In the sympathetic nervous system, we have the prolonged postganglionic nerve fibers, and the sympathetic nervous system innervates all the heart, the both ventricles and the both atria. That's why the sympathetic nervous system affects to all processes, to all, they regulate all effects in the heart. 5 effects in the heart. At the end, this is the secretion of the noradrenaline and effects to the beta-1 adrenal receptors. Beta-1 adrenal receptors. First of all, if the sympathetic nervous system innervate the both atria without innervation of the parasympathetic nervous system, it increases the force. The power of the heart contraction, and increases the tone during the diastole, a little bit increase of the muscle tone, positive inotropic and positive tonotropic effect. What is the ionic mechanisms of all these effects? At the sinoatrial node, you see in one cell, a typical myocardium cell of the sinoatrial node. This is the curve of the action potential. You know that in the sinoatrial node, this is the place of the sinoatrial node, happens the slow diastolic depolarization occurs. It depends on the permeation of the calcium and sodium ions. They runs in the inner surface of the cell membrane little by little. When the negative electric charge at the inner surface, minus 60 millivolts, decreases to 40, minus 40 millivolts, starts the fast depolarization, rapid depolarization. It depends on the permeation of the sodium ions. You know this. And then will be the repolarization. This is the stop of the influx of the sodium ions, and the outflux of the potassium ions happens. Then the electric charge at the inner surface reaches again minus 60 millivolts, and next slow diastolic depolarization happens. What do the parasympathetic nervous system with the help of the acetylcholine? The acetylcholine, this is the acetylcholine, it inhibits, this is, you see, this is the cross on the cross on the arrows, which shows the permeation of the calcium and potassium ions. That's why the channels to these ions are closed, and the rate of the slow diastolic depolarization will be is less, it decreases, and the more time need to reach the critical level of depolarization, and the action potentials will start, but through in more time. That's why the frequency decreases. This is the negative chronotropic effect. The sympathetic nervous system, it affects first of all to the both ventricles, and I present to you, this is the action potential in one typical myocardium fiber in the ventricles. It may be in the right or in the left ventricle, in one cell, in one typical myocardium fiber. This is the rest membrane potential when the excitation conducts through the sinoatrial node, through the bundle of His Purkinje fibers, reaches this typical fiber, starts the depolarization, then will be the repolarization. Depolarization is based on the permeation of the sodium ions. Then repolarization happens. This is the outflow, the potassium ions. And in the middle of this repolarization happens the permeation of the calcium ions. One ions moves out the cell, the other positive ions moves in the cell. That's why it increases the time of the repolarization. This is the start fast repolarization, beginning fast repolarization, final fast repolarization, and this is the plateau or slow repolarization. It is based on the formation of the calcium ions. What do the noradrenaline? Noradrenaline increases the more channels to the calcium ions, and the duration of the action potentials becomes more. This is the dotted line, shows that this is the more duration of the action potential. These calcium ions help to interact between the actin and the myosin fibers. That's why the force increases of the heart contraction according to the more permeation of the calcium ions in the myocardium typical cells. At the same time, the sympathetic nervous system and mediator noradrenaline, which affect to the beta-1 adrenal receptors, increases the rate of the slow diastolic depolarization. This is the first line, depends on the noradrenaline. It increases the permeation of the calcium ions and the frequency increases. This is the positive chronotropic effect. At the below part of this picture, you see this is the Bernard experiment. At the next picture, I present the same. This is the Bernard experiment. Claude Bernard, this is the French physiologist who at the middle of the 19th century investigated the role of the autonomic nervous system innervation of the vessels, not the heart, but the vessels. And he take the white rabbit with white skin and with white hair, and at the beginning of the ear, you see this is the 2 ears, the face of the rabbit, and 2 ears. He cut off the nerve. He didn't know what is this nerve, but later he investigated that it was the sympathetic nerve. In 2-3 minutes, this this ear, one ear, becomes red after this cut and have the more weight and move down at the side of the head of the rabbit. That's why the conclusion from this experiment: under normal condition, the sympathetic nervous system a little bit contracts all the blood vessels. Without influence of the sympathetic nervous system, the blood vessels relaxes and the more blood flows from the arteries, from the aorta to the capillaries, and the more blood will flow to the viscera. At what part of the blood vessels affect the sympathetic nervous system? You see, this is the curve, white curve. This is normal distribution of the blood pressure in the different parts of the vascular bed. This is the, in the aorta, systolic pressure 120 millimeters of mercury, systolic, and the diastolic. You see, this is the waves, anacrotic, catacrotic, decrotic increase, then the blood pressure decreases normally. And in the vena cava, it is near the 0, 1-2 millimeters of mercury. It depends on the resistance, vascular resistance. I remind you, what is the vascular resistance? This is the friction between the, first of all, proteins in the plasma and the side wall of the all vessels. And normally, before the capillaries, this is the 50% of the vascular resistance. The sympathetic nervous system doesn't innervate the aorta. It doesn't influence to the capillaries. It doesn't influence to the veins. It contracts the small arteries and the arterioles before the capillaries. And the vascular resistance increases from 50 to, this is only example, to 75%. In other parts of the vascular bed, the vascular resistance start to decrease. This is from 35 to 25. This is from 5 to 2%, and so on. That's why the sympathetic nervous system, its effect with the help of the noradrenaline to the alpha-1 adrenal receptors and contracts these small vessels, and the blood pressure in the large arteries and in the aorta increases according to it is based on the increase of the vascular resistance. It becomes, this is example, 140 to 100, and then it starts to decrease. But the pressure after this contraction of the small blood vessels will be lower than before this contraction. That's why the blood flow will be decreased. It happens not in all body. The sympathetic nervous system affects to the the blood vessels in the gastrointestinal tract, to the kidneys, and to the subcutaneous tissues in the skin. And in the other places, the sympathetic nervous system affects with the help of the same mediator noradrenaline to the beta-2 adrenal receptors. It happens in the vessels of the brain, of the heart, and in the skeletal muscles, and they are relaxes. That's why the result of this effect, this is the redistribution of the blood flow. The more blood flow goes to the brain, to the heart, and to the contracted skeletal muscles during the physical work. And the blood flow decreases in the gastrointestinal tract, in the kidneys, and in the subcutaneous tissues. It helps to produce the more normal work of the brain and in the heart, at the emotional stress and in the physical stress. At this part of this figure, you see the plan of the main regulation of the blood pressure. This is the heart with 4 chambers, and this is the baroreceptors. When the blood pressure in the arch of the aorta increases, it conducts with the help of the depressor nerves to the vascular motor center. And then it regulates the increases the work of the vagus nerve, more excitation, more action potential conducts to the heart, and stops the tone of the sympathetic nervous system. You see, this is the blue crosses. The vessels are relaxed, the sympathetic nervous system doesn't affect to the heartbeat rate decreases, and the blood pressure decreases. It happens only during the increase of the arterial blood pressure. At this picture, this depressor reflex I mark with the English letters. This is the heart, this is the blood pressure, it is increased. This is the baroreceptors, they are localized in the all arteries, but the more concentration happens in the arch of the aorta and in the bifurcation of the synocarotid arteries. The excitation conducts to the direction of the brain with the help of the depressor nerves. depressor nerve. And this is the body of this dendrite. This is the axon, and this is the vascular motor center. The main part of the vascular motor center is located in the midbrain, and it have the two departments: the depressor department and pressor department. This is a letter P, pressor department. Depressor department decreases the blood pressure, pressor department will be increase the blood pressure. Depressor department increases the excitation increases in the depressor department, and the excitation conducts to the center. It is near the vascular motor center, the center of the vagus nerves, and excitation conducts and results in the negative chronotropic effect, negative bathymotropic, dromotropic effects. At the same time, the vascular motor, the pressure part of the vascular motor center start to decrease this excitation. This is the reciprocal interrelation between the depressor and the pressor center. When this increases the tone of the pressor center decreases. It inhibits the excitation conduction along the sympathetic nerve fibers, and the work of the heart will be decreased, and the pressure will be normalized. This is the increase, and this is the result, the normalization of the blood pressure. It doesn't decrease to the zero. It decreases to the normal level, 120 and 80 millimeters of mercury. At the same time, the excitation doesn't conduct to the blood vessels. It starts to relax. At this plan, you see the functional system. The depressor reflex, this is the main part of this functional system. But the blood pressure, this is the main part. This is the systemic creating factor. This is the blood pressure, 120 and 80 millimeters of mercury. Depends on a lot of the processes. The depressor reflex, this is the main fast regulation of the normalization of the blood pressure at the emotional stress or very hard physical work. But it may be regulated with the hormones, adrenaline, vasopressin, kinins, histamine, and so on. What we see at this picture, blood pressure. Blood pressure may be increases, decreases according to the change of the functional processes in the body. And it results in the stability of the M. This is the metabolic processes in all viscera. It stabilizes the biochemical reactions. This change these changes of the blood pressure stimulates the vascular receptors. The vascular receptors are located, first of all, in the aorta, in the carotid bifurcation, and in the other arteries. Then excitation conducts. This is the nervous pathway to the vascular motor center. Here, this is the vascular motor center. This is the principal picture. This is the more precise anatomic picture of the same processes. And at the same time, the blood flows in the brain and stimulates the vascular motor center. The capillaries, with more pressure, stimulates the neurons in the vascular motor center. This is the central nervous system. First of all, this is the brain. And then the excitation conducts to the hypothalamus and to the cerebral cortex. What do the central nervous system? It processes the information and makes a decision how to normalize this blood pressure. It may be normalized with a lot of the processes. The change of the heart work, positive or negative effects. The change of the tone of the blood vessels, contraction or relaxation of the blood vessels, change of the amount of the blood in the blood vessels, hemoproduction, hemodistraction, Excretion processes in the kidneys may influence to the amount of the blood. The poor organs, you know that a half liter of the blood is served in the liver, in the spleen, and for 500 milliliters depot in the liver, and maybe more or less amount of the blood in the depot organs. And the same, this is all these processes in the body, but maybe the behavior after the running, the sportsman may sit on the ground, on the chair, and have a rest, and it will be normalize the blood pressure. This is it is known the functional system of the stability of the blood pressure. And the next, the last part is devoted to the property of the baroreceptors. This is not the curve. This is not the graph. This is the plan, the theoretical plan. This is the blood pressure, and this is only the systolic, the maximum pressure. In millimeters of mercury, 120, this is normal, 140, more 200 millimeters of mercury. And we tell about some situation. First of all, this is the rest. The first at the sitting position on the chair, and the maximum blood pressure at the healthy body will be 120. These 3 points shows the excitation of the baroreceptors in the arch of the aorta, for example. And what will be? This is the rest and the picture. This is the change of the blood pressure, 120 and 80 millimeters of mercury. Anacrota, it depends on the systole of the heart. Then happens the outflow of the blood from the heart to the direction of the viscera to the capillaries. It is known catacrota. Then, you know, this is the incisura and decrotic increase when the blood rebounds from the aortic valves. And what we may register in the depressor nerve, this is the depressor nerve. We will see the summation of the some action potentials. This is the nerve impulses. The amplitude is the same because the action potentials depends on the law of all or none. But they appears in the depressor nerve only when the pressure have the maximum value, 120 millimeters of mercury. And this information inform the vascular motor center that this is the normal blood pressure. Then the next situation, this is the work, the physical work. And the pressure start to increase according to the increase of the tone of the sympathetic nervous system, and the more number of the baroreceptors start to excite. This at this level 120 and a level 140 millimeters of mercury. That's why the first property we see of this, we see this is the empty circles, What is this? This is the baroreceptors, but they are not excited. That's why our body has a lot of the baroreceptors, but they have their different excitability, and it depends on the different stimulation threshold. One portion of the baroreceptor are excited at the pressure 120, the other at the pressure 140, and the last 200 millimeters of mercury. Under normal condition, only the small portion of the vascular receptors are excited. At the physical work, the more combination, the more number of the baroreceptors are excited. and we see what we will register at the depressor node. This is the work. This is the work. The pressure becomes 140 and 90 millimeters of mercury. And we see more number of the action potentials. What are these sticks? This is the nerve impulses or action potentials. Why we don't see the depolarization and repolarization? Because we register this here and here. We register with the slow rate of the registration. If we register with more rate, each stick will present us the depolarization and the repolarization, and becomes like the picture of the action potential. Then this is the stress, the more prolonged physical work or the emotional stress. The blood pressure increases according to the more tone of the sympathetic nervous system, more tone, and it reaches 160 millimeters of mercury. And what we will see, this excitation I showed to you help to produce the depressor reflex, and in some minutes, 3-5 minutes, the pressure will be normalized with the help of the depressor reflex. The same will be at the emotional stress. But what we will see, sorry, one moment. What we will see with the picture of with the action nerve impulses in the depressor nerve. This is the emotional stress. The pressure is equal to 160 and 100 millimeters of mercury, and we will see a very high frequency of the action potentials of the nerve impulses. Why we don't see the more number of the patterns of these action potentials? They are summarized in a lot of the action potentials, because it depends on the second property of these baroreceptors. The frequency of the action potentials, this F frequency of the action potentials, depends on the baroreceptors, the systolic baroreceptors, not linear, it has no linear dependence. This is the square dependence. Frequency depends on the blood pressure in square. This is the quadratic equation. That's why appears a lot of the action potential, and it helps to produce the depressor reflex. And in some minutes, maybe 3, 5, 10 minutes, the blood pressure will be normalized. This is the healthy body. But during the prolonged stress, during some hours, during some days, very hard work, emotional stress every day, what will be? When the blood pressure doesn't decrease to the normal level, these baroreceptors starts to stop to produce the action potentials. This is known accommodation, and the number of the excited baroreceptors decreases, and you see the level becomes more, 180 millimeters of mercury, and you see at the prolonged stress, this is the picture, 100 of the blood pressure, 180 and 110 millimeters of mercury. But we will see the same again, the picture like this picture, because they have the adaptation. That's why the baroreceptors have the 3 properties from this picture. It maybe don't askable at the exam, this picture, but the property, this question happens in the exam tickets. You may answer with the help of your notebook, but without notebook, this is 3 properties. The baroreceptors have the different stimulation threshold and different excitability. Not all the baroreceptors are excited at the same time. One at the 120, the other at 160, the last at 200 millimeters of mercury. The second property, the second feature, at the prolonged stress, they are excited very rapid, because this is the quadratic equation between the frequency, the number of the action potential, and the blood pressure. And the third that it happens the accommodation of these baroreceptors. Thank you for your attention. We finish. All right.